This video serves solely for educational and informational purposes. While every effort is made to ensure accuracy,
Welcome to our quick overview of aerospace engineering. In the next few minutes, we'll break down the essentials of this fascinating field. When we look up at the sky, we often see clouds, the sun, the moon, maybe a few stars if we're lucky. But what we don't always see are the incredible feats of engineering that allow us to explore that vast expanse. We're talking about airplanes, rockets, satellites, all products of aerospace engineering. It's like taking all the coolest parts of physics, chemistry, and math and using them to build things that fly. So buckle up, space cadets, as we embark on a journey to understand the core principles of aerospace engineering. Let's start with the fundamental force that allows heavier-than-air objects to take flight: aerodynamics. Imagine holding your hand out of a moving car window. You feel the wind pushing against it, right? Now imagine shaping your hand just right so that the air pushes it upwards. That, my friends, is lift, and it's the key to flight. Aerospace engineers study how air, a fluid, interacts with objects in motion using complex equations and wind tunnel experiments. Streamlining, the sleek designs you see on airplanes and rockets, helps minimize drag, allowing for more efficient flight. It's a delicate dance between lift, drag, thrust, and weight, and understanding this interplay is at the heart of aerospace engineering. So we figured out how to generate lift and minimize drag, but how do we actually get these massive machines moving? That's where propulsion comes in. Think of the roar of a jet engine or the fiery blast of a rocket launch. Jet engines mix air with fuel and ignite it to produce hot exhaust gases, propelling the aircraft forward. Rocket engines carry their own oxidizer, allowing them to operate even in the vacuum of space. Now imagine building a structure that needs to withstand extreme temperatures, intense pressure, and the forces of gravity. From the aluminum alloys that form the fuselage of an airplane, to the heat-resistant tiles that protect the space shuttle during re-entry, material science plays a crucial role. Composites like carbon fiber are becoming increasingly popular due to their incredible strength-to-weight ratio. Chapter 4. Flight Mechanics, the physics of flying. We've got lift, thrust, and a sturdy structure. Now, how do we actually control this thing? Flight mechanics is essentially the language of motion for aircraft and spacecraft. Think of an airplane's control surfaces: the ailerons on the wings, the elevators on the tail, and the rudder. These surfaces allow the pilot to manipulate the airflow around the aircraft, controlling roll, pitch, and yaw. Understanding the orbits of satellites and planning interplanetary trajectories also falls under the umbrella of flight mechanics. Chapter 5. Control Systems, Automation in the Skies. Piloting an aircraft manually requires incredible skill and precision. But what if we could automate some of these tasks, making flight safer and more efficient? That's where control systems come in. These systems, often involving complex algorithms and feedback loops, help stabilize and navigate the aircraft or spacecraft. Control systems are essential for everything from reducing pilot workload to enabling autonomous flight and exploration. Chapter 6. Spacecraft Systems, Surviving the Final Frontier. Venturing beyond Earth's atmosphere presents a whole new set of challenges. Spacecraft systems encompass the unique technologies required to operate in the harsh environment of space. Without air to provide resistance, spacecraft rely on thrusters and precise calculations to maneuver. And let's not forget about the extreme temperatures of space. Thermal control systems using insulation and heat pumps are crucial for keeping the spacecraft and its instruments within operational limits. Chapter 7. Avionics, the electronic nervous system. Just like we rely on our nervous system to sense and respond to our surroundings, aircraft and spacecraft depend on avionics, their electronic nervous system. This encompasses all the electrical systems used for communication, navigation, and control. Communication systems, from radios to satellite links, are vital for keeping pilots connected with air traffic control and mission control centers. Chapter 8. Environmental Considerations. Engineering for a Sustainable Future. As we continue to push the boundaries of aerospace engineering, it's crucial to consider our impact on the environment. Noise pollution, A significant concern around airports is being addressed through the development of quieter engines and aircraft designs. Fuel efficiency is another major focus, with engineers constantly working to reduce emissions and fuel consumption. Chapter 9. Applications. From everyday flights to cosmic explorations. Aerospace engineering underpins so many aspects of our modern world. From the commercial airplanes that connect us across continents to the military aircraft that protect our skies, aerospace engineering plays a vital role in transportation and defense. Satellites that beam back data about our planet, telescopes that peer into the depths of the universe, and spacecraft that venture to other planets are all testaments to the power of this incredible field. And who knows, maybe one day, thanks to the work of future aerospace engineers, we'll be traveling to the stars. Outro, keep exploring. Thanks for joining us on this quick journey through aerospace engineering. We've covered a lot of ground, from the principles of aerodynamics and propulsion to the complexities of spacecraft systems and avionics. Aerospace engineering is a constantly evolving field, always pushing the boundaries of what's possible. Stay curious and keep exploring the skies and beyond. Who knows what incredible discoveries await us in the vast expanse of the cosmos?